In this video we're going to talk about phase shift oscillators, which are oscillators that use a few poles to set their loop gains to -1. We're going to start with a brain teaser. Pause the video and try to analyze whether it's possible at all for this system to oscillate. And assume you can pick whatever R, C, R1, and R2 values you want in order to achieve that oscillation. This is asking you to solve a problem that you haven't seen before, so think about what you know about loop gain to try to answer the question. The answer is yes, it's possible for the system to oscillate. Getting to that answer relies on a bit of analysis, and we'll kick that off with this block diagram. We found the loop gain that lives in this block by multiplying the gain of each op-amp. So 1 for the two unity gain op-amps, and minus R1 over R2 for this inverting op-amp. And then also multiplying the transfer function of each of these RC dividers. And that's going to wind up with 1 over RCS plus 1, and there's 3 of them, so it's cubed. The system is drawn in unity gain feedback here, and that's because it's in unity gain feedback here. We just have a wire from the output of the third stage back to the first one. However, this block diagram looks a little funny, because the summing junction doesn't have a negative sign. It also doesn't have an input, but that's normal for an oscillator. So that means this system looks like positive feedback around a negative loop gain. So that means we should factor the -1 out of the expression in our block here in order to define our loop gain as R1 over R2 over RCS plus 1 cubed. And that minus sign gets eaten by the summing junction in order to make sure that our system has overall negative feedback. In negative feedback, the closed loop transfer function is L of S over 1 plus L of S, as we've seen before. So we want L of j omega to be equal to -1 to have oscillation. We have 3 poles, so that means we can get a phase of up to -3 pi over 2, and we can pick some frequency where the total phase is -pi. Then you just pick R1 over R2 to make sure your total magnitude is equal to 1. So yes, we can make this oscillate. We can achieve getting L of j omega equals -1. It's worth noting that this analysis hinges on the phase of the loop gain, while the magnitude is something that we feel like we can just correct as an afterthought. That's an insight that should guide the analysis of most oscillators. The phase of the loop gain is hard to change, so it determines whether a circle will oscillate, while the magnitude of the loop gain is relatively easy to tune, so it often isn't a deciding factor in whether you can get something to oscillate. Okay, so we're going to do this again with a new circuit. Pause the video and figure out whether it's possible for this circuit to oscillate. Note that the only thing that's changed relative to the last slide is that the first op-amp is a non-inverting amplifier instead of an inverting amplifier. This circuit can't oscillate, which you might find surprising because it's in positive feedback. You've probably been taught that positive feedback is a recipe for instability, but it's not a guarantee of oscillation. That said, we found this block diagram the same way as the block diagram on the previous slide, just the inverting gain of minus R1 over R2 has been replaced by the non-inverting gain of 1 plus R1 over R2 in the numerator here. And we have the same 3 co-located poles. Like before, this is in positive feedback. This wire comes around to the plus terminal. And so we don't have a negative sign on our summing junction. That means our loop gain is just the contents of this block in the block diagram. But because there's no negative sign to start with in our loop, and we can't provide one in our loop gain, we're in net positive feedback. So the closed loop gain of a system in positive feedback is L of S over 1 minus L of S instead of 1 plus L of S down here. And so you need L of j omega to be equal to +1 in order for this system to oscillate. And you would need a 4th pole to do that. There's no way you can get 360 degrees of phase out of this expression. So we're going to go back to the circuit that we know can oscillate, which is called a phase shift oscillator for reference. We'd like to figure out what values of R1 and R2 we should use to make this oscillate, and we'd also like to know what frequency it will oscillate at. I've copied our loop gain and oscillation condition over here for reference. We're going to start by noting that because all of our poles are in the same location, they each have to contribute equally to the desired phase of minus pi degrees, minus pi radians. That means each pole will be contributing minus pi over 3 radians of phase at our frequency of oscillation. We can look at our transfer function for just one pole, which is given by an impedance divider between R and C. I introduced the variable omega pi over 3, this 0.33 pi down here, which is the frequency at which the pole contributes minus pi over 3 radians of phase. By definition, we know the angle of each one pole at the frequency, pi over 3 frequency, is minus 60 degrees, or minus pi over 3. But it also has to be equal to the inverse tangent of omega pi over 3 times RC, just by evaluating the angle of this expression. So the inverse tangent equals 60 degrees when the argument here is radical 3, and you can remember that by digging deep and going back to a 30, 60, 90 triangle. So we know that our omega pi over 3 has to be equal to root 3 over RC. We can take the magnitude of our loop gain at that frequency in order to figure out what gain we need to set it to 1. So the RC in our omega pi over 3 down here cancels out with the RC in our H1 pole transfer function. And then we square this radical 3 and add it to 1 and take the square root in order to find that the magnitude per pole is 1/2, and we have 3 of them stacked on top of each other. So our overall loop gain is R1 over R2 times 1/8. That means R1 over R2 needs to be 8 for oscillation. And the frequency we'll oscillate at is omega osc equals omega pi over 3. So this root 3 over RC frequency. We can compare this loop gain analysis to a root locus plot. The root locus for 3 co-located poles is given by these 3 lines sort of flying away at equal angles. And so it's believable that if you crank up the gain enough, say to 8, you'll wind up with 2 of those poles living on the j omega axis. So in summary, linear systems will oscillate if the poles are on the j omega axis, and that's the same condition as L of j omega being equal to -1 if the system is in negative feedback. We can design the gain of amplifiers in feedback to achieve L of j omega is equal to -1. And the classic example is the phase shift oscillator, which is pictured here along with the desired gain, 8, and the oscillation frequency, root 3 over RC.